I want to thank the organizers for holding this conference remotely and that they accepted my talk. Let me introduce myself. I'm Robert McLay. I'm from the University of Texas, and I work at the Texas Advanced Computing Center, or TACC. I've been working at TACC since 2008, and I've spent much of this time working on tools. I am the developer of Lmod, a modern environment module system, and the tool I'm going to talk about today, XALT, which is a tool which allows you to job level usage data on your supercomputers. A colleague of mine at TACC designed the logo for XALT. You should notice there's something special about the blue eye, and I'll explain what it is when I get to the end. For today's talk, I'm just going to describe what XALT is and is not. I'm going to have a brief history. I'm going to talk about how it works in three major parts. I'm going to talk about what can you do with it and how I might help you. It can be difficult to know what your users are running on your system. We know from accounting how much each team used our resources, but not what they did or what libraries they used or what executables they used. XALT is a way to learn what your users are doing on your system. So from XALT, we can find out what programs or libraries what programs and libraries your users are using. Say that 3 times fast. What imports from R, MATLAB, or Python? What are the top programs by core hours, by counts, by users? Since we know something about the executables and where they came from, were they system executables? Were they built by staff? Or were they user built? Or were they built by other users? Are the executables implemented in Fortran C or C++? We can track the number of MPI tasks or threading. We can learn something about functions. But XALT is a census taker. It's not a performance tool. There are plenty of other performance tools out there. So XALT is there to just see what's running because it's running all the time. A brief history. XALT was funded by the National Science Foundation to Mark Fahey and myself. This project's funding has been completed, but work has continued at TACC because it's been too useful for us. Originally, it only tracked MPI executions. Since XALT is being attached to every job, every execution on the system, we need it to be extremely lightweight. But we want to know what libraries or applications are used, what functions are using to call built-in libraries like MPI or PETC or FFTW or BLAS and stuff like that. And then we want to collect this data into a database so we can figure out what people are doing over time. So how does XALT work? Well, it breaks down to these 6 major steps. There's an LD wrapper, so we can augment the linking phase. And then we're going to use an ELF trick to actually track execution. XALT will add a signal handler so we can capture jobs that terminated abnormally. Both the linking and the running are going to produce JSON records. And this is the part that you're installing. That's when you install XALT, you're getting that. And then staff is going to have to figure out how to move the data move these JSON records to the database. And once the database is there, we're going to try and analyze it so we can get useful information out of it. So the design of the LD wrapper is where we learn things about the executable. The XALT wraps the linker to enable tracking of the executable. The LD wrapper intercepts the user's link line, and it inserts key value pairs, which I'll show you what those are later. And it also runs the trace map output from LD, and this data is then transmitted in a JSON format. And it can optionally add code that runs before main or after main for static builds. Signal handler are registered before the signal handlers are main, so we capture sig faults, floating point exceptions, terminations, and other such things. And since it's done early, the user can override them with their own stuff. So ELF is the binary format for Linux. ELF has many hooks. XALT is using 2 of those hooks to run before and after main. So this is the smallest prototype of what XALT does. The bottom 4 lines show that the myInit function is being registered with the init array. And the myFini function is being registered with the Fini array. The init array are functions, or any functions that are added to the init array are run before main. Any functions that are added to the Fini array are run after main completes. If main abnormally terminates, for whatever reason, then the myFini array is not, the function pointers in the myFini array are not run. A useful trick is to define command line variables on the command line. In this example, the environment variable LD preload is set to the shared library XALT, or libexalt.so, which was compiled from the code that was shown in the previous slide. This example shows that running main produces the hello world messages. The line before and after come from the library. We see that when LD preload is not set, the program runs normally. This is how XALT works. XALT module defines the LD preload variable so that we can change the behavior of every executable on the system. This is a great feature, which shows how, but it presents challenges, and we'll show how XALT deals with this as we go. Once we've got this data, these JSON records, we got to do something with them. There are 3 options currently available. One is to just generate a file, which then can be processed hourly, nightly. Or you can use syslog. You can do a syslog message and then run it through our syslogd and collect the data through some R syslog magic. Or you can use curl to send the JSON record to wherever you want to receive it. Since I'm the author of Lmod, I can get it to do some help. So optionally connect paths to modules. The Lmod spider command walks the entire tree. It can build a reverse map. What I mean by that is it maps paths to modules. And so we can map programs and libraries to modules. So for example, if we find this god-awful path for an HDF5 library, we can map it to a particular version of parallel HDF5 version 1.8.14. This also helps with function tracking. Sites that use the original environment module system do not have to convert to Lmod, but they can use Lmod to build the reverse map. Just do it on the side and it works just fine. I'd also like to comment about function tracking. in that function tracking is done only at link time. There is no runtime expense for doing this. It just says that these particular functions were available, were included in the executable, not that they ever ran. My personal code has calls to PETSI, but I also have another solver, so it looks like PETSI is part of my execution, but I may or may have not used it. However, there's some complications. You need LD's XALT LD before the compiler's LD. It used to be true that LD, the bin LD was what was used, but since about GCC 6, the compiler also provides its own LD. And so you need to get XALT LD before, earlier in the path. So it will be called before the one in the compiler. Lmod supports path priority. So for example, I can prepend a path and give it a priority. This means to Lmod, that anytime there is a path, when the path gets reconstructed, the ones with a higher priority move earlier in the list. So let's give an example of that. So the XALT module is loaded here, and I'm now going to list all the places that LD can be found in the path. And so it shows that the one in XALT is found, and then the one from GCC 8.3 is found, and then the system one is found. If a user then loads GCC without doing anything else, when Lmod reconstructs the path, it puts the XALT bin directory ahead of all the other paths. And so when the GCC gets loaded, and now I try and find the LDs, it shows that the XALT one is found, then the GCC one was found, and then bin ls. And without this hack in Lmod, then it would find the one in GCC before the XALT one. So what can you do if you're not going to run Lmod and try and run XALT? There are several things you can do. You can move the compiler's LD to LDX, and then make a small change to XALT LD to find LDX, and you must do this for every compiler install. Or you can put XALT's bin directory before the compiler path in the module. And this will be fine because XALT has a magic variable which won't do anything if it's not set. So this is perfectly safe. Or you can treat every executable like it's bin ls or a commercial code like Abacus. And that is, you're not going to know who built it and other things about the information. Okay, installing XALT. It's both easy and hard. All it really does require is a configure, make, install. However, there are some pieces to make that need to make that configure step work. As I talked about, you might want to have a reverse map that maps between paths to modules, because if you're a module-based system, you really want to know about NDW Chem or VASP or PETSI or FFTW, and not some god-awful path. Each site has to have its own config.py file, which I'll talk some more about later. You also have to set up transport of the JSON records. It can either go file, syslog, or curl. And if you're going to use the provided database, you're going to want some computer, a VM, or someplace to hold the database. Or you can set up your own way to handle the data. You can take the JSON and put it in your own database. Each site must configure to match their setup. At most sites, you're only interested in recording on the compute nodes. So somehow you have to find out that you're on a login node or a compute node and not do anything on the login nodes and do something on the compute nodes. So you can use regular expression matching to, if you have some convenient way to tell that it's a login node or a compute node, or if you need to, there is a functional way you can write your own code that can make this difference if regular expressions won't work for you. You're also going to want to know what executables to track and what to ignore. This is, for us at TACC, we're mainly interested in knowing user codes and stuff that we build ourselves, our version of VASP and NAMD and our libraries, PETSI and so forth. But we're not typically interested in binls. But we might be interested in copies, move, awk, sed, Perl. And also, and I'm going to talk about this later, you're going to want to sample. That is, single executions can add up quickly and overwhelm the ability to absorb it in a database. So you're going to want to sample short-run executables, and so you have to figure out how you're going to do that. XALT uses config.py to create some header files, some lex files, and some py files during the build. It also provides the XALT configuration report C++ program to know how it's configured. So config.py, your site config file, is only used when building XALT. So on the flip side, any changes to config.py require a reinstall of XALT. This is done for speed. Do not want to fire up the Python interpreter every time. So having these regular expressions be converted into flex and compiled in make regular expression matching very quick, but it means it's hardwired into the executable. So it requires a rebuild if you want to change them. So there's three kinds of pattern matching that uses flex. There's the host name, there's path filtering, and there's environment variable filtering. Flex is used to compile the patterns. It uses a regular expression to control what to keep and ignore. These flex codes are compiled into C routines, which provide fast regular expression parsing. So here's a very small version of the TACC configuration file. So hostname patterns. Our host names are named C, 3 numbers, a dash, 3 numbers, and .tac.utexas.edu. Or we have a cray, so those ones are named NID and then 5 numbers. So those are the kind of, only on machines that's host name match those patterns are kept. Everything else is ignored. Path patterns say, these are the kind of executables I want to do something about, and I'm going to ignore the rest. So in this case, I want to know, I'm going to try and keep people that use DDT, but I'm going to skip everything that's in user bin. And then at the top, I've listed 2 things, which is Python and R. We also support MATLAB, but for space reasons, I only put the first 2. I want to mark Python and R as packages. What that means is that those I'm going to be able to track the imports. Without telling it's a package, then no package stuff is implemented. Also, environment variables. I want to throw away almost all the environment variables. Originally, XALT was very interested in being able to give a reproduction of how the code was run with all the environment variables and the command line and the libraries and all that. Wonderful. The problem is that that's just too much data. I found out that 2 billion is not that big a number. On our systems, we were producing millions of executions and recording on average 250 environment variables. Well, that got to above 2 billion very quickly, and that's just too much data. So you need to choose what environment variables are worth keeping. And in the years that I've been running XALT, I've never needed these special environment variables. I've never looked at them. And in talking to others who use it, one site it says they've used it a couple times. So reducing the number of environment variables seems to be an important thing, but that's really up to you. You get to control how you filter your stuff. I just know on a big system like ours, we need to be very careful what environment variables we keep. Originally, XALT was designed to produce a start record and end record for all executions. I thought that the filtering, getting rid of binls and stuff like that, would have been sufficient, but no. Turns out that the people studying dark energy ran 5 million executions in 2 hours on a couple nodes. And it took me 4.5 days to ingest all that data. Well, obviously that's not going to work. So we have to filter out these short run jobs. So I'm only going to generate records if they're planned to save. So the first step was all non-MPI, and I will sometimes call that scalar, executions only produce an end record. Small MPI executions sample, large MPI executions record. What does that mean? So sampling goes like this. This is site configurable. The TACC rules are for 0 to 30 minutes, you have a 1 in 10,000 chance of being recorded. For 30 minutes to an hour and 20 minutes or 2 hours, you've got a 1% chance of being recorded. And anything over 2 hours is 100% recorded. But this allows us to do things like sample how people use Perl, awk, sed, gzip, etc. Turns out that you have to do it for MPI as well, or at least we have to. It's because some users were using their short MPI programs to train a deep learning engine. So the TACC rules are, if a task count is 128 tasks, or fewer than 128 tasks, it's sampled with 0 to 15 minutes is a 1 in 10,000 chance of being recorded. 15 to 30 minutes is a 1% chance recorded. And 30 minutes or longer, it's a 100% chance of recorded. Task counts greater than or equal to 128 tasks are always recorded independent of runtime. Now, why do I have these rules? Well, there are large simulations which never terminate. They run for 24, 48 hours and they just produce restart files, and they don't care how many time steps it does. They just run till they run out of time and they restart the job from their previous restart file. So I want to capture those jobs that never terminate. So that means I'm going to produce a start record for those and no end record. But if I know that the end record, if the record for that execution has 0 time associated with it, I can use the accounting to say the end time can be found from the accounting file. This, of course, is an extra step that'll have to be done outside of the normal tools. Okay. Now I've told you about how XALT works. Let's see what we can do with it. So, for example, we had a case where a large chemistry code was using the large mem queue because they felt like they could not run with the normal parallelization. And we were able to use XALT and TACC stats to find out what programs there were. TACC stat is a tool which allows us to measure the performance on a node, and XALT can say what's running. And so we were able to find out that these users, who they were, and that they could run with less parallelization. Instead of asking for all cores to be active, they could ask for half the cores be active and got double the memory. And we could show that they didn't need all the memory. They just needed more than full parallelization would do. But other times people come to my office and want to know who's running NWChem, who's running GROMACS, who's using the GPUs. Or I want to know who's using MPI3. So I was able to find out through our function tracking to find all the MPI functions. And so a few programs were running them, a couple different users and a few number of programs. But we were able to track down and say, hey, people are using MPI3. Note that this is function tracking, which means that I am only knowing that the code has that in there. It's not that it was actually used. So let's talk about some of the cool things that are part of XALT. So I've mentioned this before, but I'll mention again. We can now track packages. We can know what R packages, what Python packages, and what MATLAB packages. There's a signal handler which allows us to possibly accept more jobs. We've got optional GPU tracking with containers. XALT has constantly improved the performance to reduce the amount of time that XALT takes up. Also, that the XALT configuration report can tell you how your system is configured. I'd like to thank James McCone and Michael Scott from IU because they developed the R part, and they do it by intercepting the imports. Really recently, I found a way to track Python packages, and it again is using the same trick. It, with help from Ricardo Muti, there's a file called sitecustomize.py. If you have a file, name that, and it's found in the Python path, then Python 2 and Python 3 will run it. And then all Pythons use this array of objects called stored in system metapath to locate the import. So you can add code there which can capture the imports. So this is pretty slick. And XALT in the configuration file allows me to add some filtering. So here are some rules that say I'm going to keep or skip something. And the first rule says if there's a path, if the path doesn't start with a slash, then I want to ignore it. Namely, I'm going to ignore built-ins. I'm going to ignore anything that starts with an underscore. I'm also going to ignore any name that has a dot in it. But I'm going to keep everything that's in .local because maybe I want to install that from a system point of view. Since I'm adding a watermark to the code, it'd be nice to be able to get it out. So I added this thing called XALT extract record, and this one reads the watermark, and it finds out who built the program, on what machine, what module was used, and when and where it was built. Here's an example of a particular code, some hello world program, and what time it was, what system was built on, what the build user was, what compiler was used, the date, and all of that, and what version of XALT was used. This has been amazingly useful. XALT has been around for a while, and we thought we were going to try running an executable on our system, but discovered that the execution was actually built on Blue Waters, and because it said the build host was from Blue Waters and not one of our systems. So this can be really useful, and it can be useful to track down how people built, because you have the list of loaded modules, so you know what modules they used to build the code. A newest feature is also the ability to track GPU usage. So with a special library from NVIDIA, XALT can know whether one or more GPUs were used. It's not a performance. And I want to thank Scott McMillan from NVIDIA for this contribution. Also, another thing from Scott McMillan is the ability to track Singularity containers with XALT. You just add some environment variables to the Singularity starter, and it just works. So XALT is doing a lot in the background. How do you know if it's working? So I've added the ability to debug XALT to see what it's doing. So if you define XALT tracing equals yes, turn off sampling so it's going to absolutely record this, then you can get information about what XALT's doing. So it tells you that the Maya init ran, it set up the signals, it didn't do any recording because this is a scalar job. It prints out hello world, and then the myFini routine is run. It tells you it's run 0 out of 1. That means it's on task 0, and there's only one. It's only one number of tasks, and it tells you the path to it. It tells you we're not sampling, so we're going to go. All programs are tracked, and then it tells you that XALT runs this XALT run submission program, which takes the data from the user code, uses some hash tables, and generates a JSON file. And this one got sent to a file, and then once it's completed, it tells you it leaves myFini, and it's done. So you can find out a lot of information about XALT. And it also, if you have bugs, I'm going to ask you to run, if you've got a bug report, I'm going to ask you to run XALT configuration report and give me an example of this so I can see what's going on. So XALT has documentation at Read the Docs. And so you can hook it up to Google Analytics. So over a year, I found where people are reading about XALT. And you can see that I've hit many of the countries, most continents, and many islands. Nobody in Iceland, nobody in Greenland, have to work on that. But North and South America, all of Europe, or most of Europe, Russia, China, India, etc. I'm really pleased with this. But it's kind of nice to know what cities it comes from, so you can see that it's obviously mainly concentrated in Europe and the United States. What this says is that somebody from that city has read the documentation over the past year. So in conclusion, I'd like to point out that you should notice that the eye has a magnifying glass in it, which shows you that Big Brother is watching. If you want to know more about Lmod, I've listed where you can get the source and documentation, and XALT can be found at GitHub, and the documentation at Read the Docs, and you can join the mailing list. And I'll be happy to take questions.